Welcome back to Keys Pre-Calculus. This is section 4.2, trig functions with the unit circle. Okay, if you recall in class, we drew ourselves a unit circle on the board, or a circle on the board, and reviewed that the equation of a circle is x squared plus y squared equals 1, where the center in that particular equation is at 0, 0, and the radius is 1 unit. So that is what we are calling the unit circle, and that's what we're going to be using to find trig functions in this section. You'll also recall we talked about the circumference of the circle, or the edge of the circle, being like a number line. If you go around it in a counterclockwise direction, you can think of it being positive, the positive part of the number line. Or if you go around it in the clockwise direction, you can think of that being the negative part of the number line. And we can call the points on the circle T. Didn't mean to do that. Let's see if I can get that to work. So I'm going to put this point on the circle, and I'm going to call it the point T, which has the coordinates x, y, because we are on a graph, a coordinate plane. Okay, now if we have an arc that comes from the x-axis coming up and stopping at T, this terminal side, then we've created an angle, theta. And if you will recall, the arc length is equivalent to theta times the radius. So therefore, theta will be equivalent to the arc length divided by the radius. But in this case, our arc length we're calling T, because if we go from this point 0 up here to this point T, that's our arc length, right? And if we divide it by the length of the radius, which is 1 unit, then we can just say that theta is equivalent to T. Therefore, the real number T is the length of the arc intercepted by the angle theta given in radians. And we're going to talk about them interchangeably right now in this particular section. Now, as that real number line, that imaginary real number line, wraps around the unit circle, each real number T on this number line corresponds to a particular point on our coordinate plane. So for example, this point right here, the point 1, 0, corresponds to a T, which also corresponds to an angle opening. In this case, it would be 0, right? Because the angle, if the terminal side was the same side as the initial side, then it would be open 0 radian. But if we come up here to the point 0, 1, we can see that this point corresponds to, we learned, a quarter of the way around the circle. And since the whole way around the circle is 2 pi, this would be a quarter of it, which would be pi divided by 2. And over here, this point -1, 0 corresponds to pi, and the angle theta would be pi radian. And then down here, the point 0, -1 corresponds to 3 pi over 2 radian. And if we came all the way back up in here to finish the full circle, it also corresponds to, the point 1, 0 also corresponds to the point, or the angle 2 pi. So, because there are infinite points T on that unit circle, or that number line, then there are infinite arcs with the length of T that are intercepted by the angle theta. So there's infinite thetas all the way around the circle. And we're going to learn a few of the most common ones today, in addition to learning our trigonometric functions. So from this discussion, it follows that the coordinates x and y are two functions of the real variable t, and we're going to use these coordinates to define our 6 trigonometric functions. So I wrote these functions up in the top left of the screen. They are sine, cosine, tangent, cosecant, secant, and cotangent. But we actually abbreviate the spelling because it would take too long to write all of that out every time. So here they are in their abbreviated form. Sine is S-I-N, cosine, C-O-S, tangent, T-A-N, cosecant is C-S-C, secant is S-E-C, and cotangent is C-O-T. And these 6 functions are defined in terms of x and y and the radius. or the hypotenuse if you're talking about a right triangle. So the sine of t, or the sine of theta, but in this case, for this section, we're going to call it the sine of t, is related to the y value, the y divided by the radius. However, since the radius is 1, it's y over 1, which is just y. Cosine of t corresponds to the x, or x over 1 in this case, which is just x, and the tangent of t corresponds to y divided by x, where x cannot equal 0 because you cannot have 0 on the denominator. Now cosecant, secant, and cotangent are inverses, multiplicative inverses of these functions. So the cosecant of t is the inverse of the sine of t, which would, instead of being y over 1, it would be 1 over y, where y cannot equal 0. And the secant of t is the inverse of the cosine of t, which is equivalent to 1 over x, again, where x cannot equal 0 because you cannot have 0 on the denominator. And then the cotangent of t is equivalent to x divided by y, where in this case y cannot equal 0. So what does this look like if I want to take the trigonometric functions of a particular angle or point on this unit circle? Let's start with pi over 2. Let's say I wanted to take the 6 trigonometric functions of the number or the angle pi over 2. So if I take the sine of pi over 2, that is the same thing as saying y divided by the radius. Well, the y value at pi over 2 on this unit circle is 1. So it would just be the number 1. So the sine of pi over 2 is 1. The cosine of pi over 2 would be equivalent to x at the point 0, 1. And since x is 0, the cosine of pi over 2 would be 0. And of course the tangent would be y over x. The tangent of pi divided by 2, I didn't give myself a lot of room there, would be y, which is 1, over x, which is 0, which is undefined. There is no tangent function of pi over 2. It's undefined. Cosecant would be 1 over y, right? Cosecant of pi over 2, if we look back over on the left, it is 1 over y, and that would be 1 over 1, which is equivalent to 1. The secant of pi over 2 will be 1 over x, which is 1 over 0 in this case, which is, again, undefined. And then the cotangent of pi over 2 would be equivalent to x, which is 0, over y, which is 1, so equals 0. So that's how you find the trigonometric functions of a particular point, or, excuse me, of a particular angle. Why don't you pause the screen, take a second to let that sink in, and try to recall how we did that. And then when you come back, we are going to find the x and y coordinates for some very common angle measurements. Okay, so you've seen I've cleared up the screen a little bit. I would like to find the x and y coordinates when t lands here, and theta is equivalent to 45 degrees, which in this case we're going to do radians, so we're going to say pi over 4. We're going to allow t to be pi over 4. We need to figure out our x and y coordinate. Here is where my triangle comes in. So if I have this right triangle, which just magically appeared, and I move it down to my central angle here, my unit circle, and its hypotenuse is the central angle that opens up to pi over 4. And you can see that my radius, because my radius is 1, then I know that my hypotenuse is 1. And because it's a 45-degree angle, and I've dropped an altitude from this point down to the x-axis, we know that this is a 45, 45, 90-degree triangle, whose sides are in relation of 1, 1, square root of 2. Now, square root of 2 is longer than 1, so that makes it the hypotenuse. But in this case, we know that my hypotenuse is 1. So if my hypotenuse is 1, then my two sides are in the relationship of 1 over square root of 2, and 1 over square root of 2. So that means that this length, and let's see if I can change my pen color here to help you see it better. Now we don't put 1 over square root of 2 because that's not simplified. We're going to rewrite that as the square root of 2 over 2. Remember, 1 divided by the square root of 2. If I rationalize the denominator, I multiply both the numerator and the denominator by the square root of 2, which is really multiplying by 1. So I get square root of 2 on the numerator, and square root of 2 times the square root of 2 gives me 2. So that means that this leg is square root of 2 over 2, and this leg is square root of 2 over 2. So that means my x length, that's one of the legs, this is the x length, is the square root of 2 over 2. So my x value up here, to get to this point, I would have to go right square root of 2 over 2 places. And then my y length is also the square root of 2 over 2. So I would come up here and go over square root of 2 over 2. So the x and y coordinates for a 45-degree angle, or a pi over 4 radian angle, is the square root of 2 over 2 x and the square root of 2 over 2 y. Now if I draw another one over here, another 45 degree 90 degree triangle in the second coordinate, it's really an angle of 100, theta would be 135 degrees because it's 90 and then another 45. So I would want to know what the coordinates for of theta when it's 3 pi, over 4. I don't think I said that very clearly. When I am looking for theta 3 pi over 4, where does it land? It lands right here, and where the pink dot is. And I want to know what the x and y coordinates are for that. Well, because it's a 45, 90 triangle, again, right here, this is 45 degrees, or pi over 4 degrees, then I have the same x and y measurements, because this length right here is pi over square root of 2, over 2, but it's in the negative direction, and this is square root of 2 over 2 in the positive direction. So my x, in this case, is going to be negative square root of 2 over 2, and my y is going to be positive square root of 2 over 2. Now I would like for you, for your homework on the unit circle that you already started filling out, to find the coordinates for 5 pi over 4 and 7 pi over 4. And bring that to class on Tuesday. Now we're going to move on to some other common angles. We're going to stay in the first quadrant for the video because you're going to find the angles in the second, third, and fourth quadrant for homework. And particularly, we're looking at the central angle of theta equals 30 degrees, or pi over 6 radian. And theta, didn't mean to put a comma there. Theta is equivalent to 60 degrees, which is pi over 3 radian. You can see I cleaned up the graph, and I took off pi over 3, and I put a 30, 60, 90 triangle where theta is for pi over 6, or 30 degrees, where theta is the pi over 6, or the 30, and then you've got a 60 and a 90. And if you recall from your geometry, a 30, 60, 90 triangle is in the relationship of 1 to square root of 3. Their sides are in that relationship, or that proportion. Now, because the hypotenuse is across from the right angle, and we know the hypotenuse is 1, if the hypotenuse here is 1, then which is half of 2, then everything else is going to be halved. So it would be square root of 3 over 2, and 1/2 will be my sides. So my side length here, to get to this long value right here, the one that is across from the 60 degree angle, it's going to be square root of 3 over 2, that length. And this length up here, across from my 30, or my pi over 6 degree angle, is going to be 1/2 length, because this is a 1. So the coordinates here, my x value would be the square root of 3 over 2, and my y value would be 1/2. So those are the coordinates for a pi over 6 degree theta, or angle. Up my circle a bit and moved my 30, 60, 90 relationship over to show you, and then I added another triangle, and I added another 30, 60, 90 degree triangle. But this time, we're looking for the 60 degree angle, or the pi over 3, which is, so my theta is going to be the 60 degree, or the pi over 3 angle that's right here. So this theta, pi over 3 radian. So in this case, my x value would have to be across from the 60 degree angle, or not the 60 degree, the 30 degree angle, or the pi over 6 degree angle. So it would be 1/2. And my y value, or how much I go up, would be across from the 60, or the pi over 3 degree angle, which is going to give me square root. Whoops, that's in a bad place. Let's see if I can redo that there. Which would be the square root of 3 over 2. And then my radius is 1. So this x, y coordinates of pi over 3 radian would give me, my x would be 1/2, and my y would be the square root of 3 over 2. So that's how you find the coordinates of a 60 degree or pi over 3 radian theta, or angle, or where t lands on the number line and creates that arc. So I would like for you, for homework, to finish filling out the rest of the unit circle chart by creating the coordinates for 2 pi over 3, 5 pi over 6, 7 pi over 6, 4 pi over 3, 5 pi over 3, and 11 pi over 6. Because we've done all of the other ones together, or you've done them for homework. And so finish filling out that chart, and then you can use it for your homework. Let's do an example. If I said find the 6 trigonometric functions of 3 pi over 4 radian, then you would go back to this unit circle. You could see that we've already solved this one. We've found the coordinates for 3 pi over 4, which is in the second quadrant. And we know that it's the negative square root of 2 over 2 for x and the positive square root of 2 over 2 for y. Since the sine of t, or the sine of 3 pi over 4, is the y value, then we know that the sine of the square root of, sine of 3 pi over 4 is the square root of 2 over 2. And because the cosine is the x value down here, so that was, the sine is the y value, the cosine is the x value. In this case, it's negative square root of 2 over 2. And then the tangent is going to be, of 3 pi over 4, is going to be the y value, which is the square root of, let me see if I can move that down a little bit. The square root of 2 over 2 divided by the negative square root of 2 over 2, because it's y divided by x, which that reduces to negative 1. And then we just take the reciprocals. The secant is going to be 1 over y, or 1 over the square root of 2 over 2. Well, I'm going to do some work over here. 1 divided by the square root of 2 over 2 is the same thing as saying, remember when you're dividing fractions, don't ask why, just flip the second, multiply, so it's 2 over the square root of 2, which in this case we want to rationalize the denominator, so we get 2 square roots of 2 over 2. Those 2's, whoops, sorry about that, those 2's cancel each other out, so it's really just the square root of 2. So the secant of 3 pi over 4 is the square root of 2. And the cosecant of 3 pi over 4 is the reciprocal of the negative square root of 2 over 2, which would then be the negative square root of 2. And then the cotangent is the reciprocal of negative 1, which is negative 1. So you'll see that reciprocal functions have the same positive or negative value. In fact, that's another thing that I want you to find on your unit circle is, in the first quadrant, what is the positive and negative value of all of the 6 trigonometric functions? In the second quadrant, what are the positive and negative values? What will they always be of the trig functions? In the third quadrant, the same, and in the fourth quadrant, the same. We can see, because our x and y values are both positive active in the first quadrant, that there's always going to be sine is positive, cosine is positive, tangent is positive. We know that, and so therefore cosecant positive, secant positive, cotangent positive. And we can also see over here in the second quadrant, because our x value will always be negative and our y value will always be positive, that sine will be positive, cosine will be negative, and cotangent will be negative. Excuse me, sine will be positive, cosine will be positive, tangent will be, I said that all wrong. Sine is positive, cosine is negative, tangent is negative, and they're reciprocals. Secant is positive, cosecant is negative, cotangent is negative. But you can find it out for quadrants 3 and 4. And record that on your unit circle for class on Tuesday. I'm going to give some of your work away here, but I want to do another example with you in the negative direction. So if I said, find the 6 trig functions of negative pi over 3, we're going to figure out how to do that together. So basically I'm going to start here at 0, and I'm going to go in the negative direction, pi over 3 theta, or radians, okay, when theta is pi over 3. So it would be this point here. Now, it's equivalent to negative 60 degrees, so I'm going to have the same 1/2 as my x and square root of 3 over 2 as my y. However, my y is going in the negative direction, so it will be negative square root of 3 over 2. Because sine of theta, or sine of t, is the y value, or y over the radius, which in this case, the unit circle, the radius is 1, so it's just y. Then I look at my y value, and in this case, the sine of negative pi over 3 is the negative square root of 3 over 2. And the cosine of theta is going to be the x value. The cosine of negative square root of 3 in this case would be positive 1/2 because x is still going in the positive direction. Now my tangent is going to be y over x. So I have negative square root of 3 over 2 divided by 1/2, which is the same thing as saying the negative square root of 3 over 2 times 2 over 1. The 2's cancel each other out, and I'm left with just negative square root of 3. We need to find the reciprocal functions. Cosecant is the reciprocal of sine, and since the sine of negative pi over 3 is the negative square root of 3 over 2, the cosecant of negative pi over 3 would be 2 over the square root of negative square root of 3, which when I rationalize the denominator, I multiply both the numerator and the denominator by square root of 3 over 3, and that ends up becoming 2 square roots of 3 over 3. And of course the reciprocal of cosine is secant, so I just take 1/2 and I take its reciprocal, which would be 2 over 1, which simplifies to 2. And then the reciprocal of tangent is cotangent, and when I take 1 over the negative square root of 3, I get negative square root of 3 over 3. And the cosecant up here, because sine is negative, cosecant should also have been negative, so I should have made that a negative. All right, you see how that works? Let it sink in for a second. Now we need to talk about domain, range, and period of sine and cosine. We'll worry about the other trig functions later. Now, domain, remember, is the input value, so that would be the t value. And you can put anything you want in for t. So the sine of t, the cosine of t, you can put anything you want. So t, the domain of both sine and cosine, is going to be all real numbers. But the output values are y's and x's. And those are different. So if you look in the unit circle that I have up here, you can see that your x value goes from negative 1 to 1. And your y value also goes from negative 1 to 1 in the unit circle. So because negative 1 is less than or equal to y, which is less than or equal to positive 1, this part of the range would be the sine part of my range. So the sine of t. Whoops. Sorry about that. I need to write the whole word sine here. The sine of t is going to range between negative 1 and 1. And because the x values also go from negative 1 to 1, the cosine value, the cosine range, is going to go from negative 1 to 1. My input values or domain of sine and cosine are all real numbers, but my output values of sine and cosine are going to range between -1 and 1 for both the x and the y. Something else to keep in mind is that because the circle is periodic, I can go around the circle, well, let's see if I can draw this, infinite times. My period, or I should say it's periodic, and my period ranges from, I can start at 0, including 0, to 2 pi, but then I can go around again for another 2 pi, and I can go around again for another 2 pi, and again till infinity. I can keep going around 2 pi to 2 pi to 2 pi. We talked about terminal angles in class, remember? So if I've got a theta that is right here, I could also have another theta that lands in the same spot, but it's gone around an extra 2 pi times. So this theta is right here. Or I could have another one that goes around 1, 2, 3 times, or twice more, and then lands there. So my blue theta has an extra 4 pi added to it. Let's pretend that this pink angle here, theta, is pi over 6. It's not, but let's pretend that it is. So I know its coordinates are going to be the square root of 3 over 2 and 1/2. So the sine of pi over 6 is the y value, so it would be 1/2. The sine of pi over 6, if it's the green theta, if it goes around again, it would be pi over 6 plus 2 pi, which ends up being 13 pi over 6, correct? And that would be the same thing because it lands in the same place. It's coterminal angle, or coterminal side, so it would also be 1/2. And if I even went around again, and I went around twice, it'd be pi over 6 plus 4 pi, which gives me 25 pi over 6, but it would also be 1/2. So you can see that every time it lands in the same spot, that angle lands in the same spot as pi over 6, it's going to have the same output value as pi over 6. Sine and cosine, or actually all of the trig functions, are periodic, which means f of t plus some period, some cycle, is equivalent to f of t. And the period of sine and cosine is 2 pi because it completes one circle in 2 pi radian. Therefore, the sine of t plus 2 pi times n is the number of times it goes around, is equivalent to the sine of t. And the cosine of t plus 2 pi times however many times it goes around is equivalent to the cosine of t. Sine and cosine are periodic functions with a period of 2 pi. Their domains are all real numbers, and their ranges go from -1 to 1 for y and -1 to 1 for x. Now let's go backwards with it. If I said evaluate sine of 13 pi over 6, then I could look at that and say, I know that 13 pi over 6 is greater than 2 pi. So I can rewrite it as sine of 2 pi plus some number to give me 13 pi over 6. And that, when I take the sine of that number, because sine is periodic, I can take the sine of this missing number here that's less than 2 pi, and I will have my answer. So the way I do it is I say 13 pi over 6 minus 2 pi, which is the same thing as saying 12 pi over 6, right? Because 12 pi over 6 divided by, or 12 divided by 6 is 2. So that gives me 1 pi over 6. So 13 pi over 6 is the same thing as saying 2 pi plus pi over 6. And the sine of pi over 6 is 1/2, as we saw earlier. I can find the sine and cosine of angles bigger than pi over 2 by subtracting pi over 2n from them and then evaluating them at their coterminal angles.
We will talk about even and odd functions in class on Tuesday. You have enough to do your homework now. Have a great weekend. Rather, I should say, enjoy what's left of your weekend.